At 13:49, climbing north from Puerto Vallarta, Alaska Airlines Flight 261 made a small trim adjustment. The horizontal stabilizer in its tail moved less than 0.2 of a degree. Then it stopped. For the next 2 hours and 20 minutes, a flight control meant to move throughout the journey remained fixed in place. The pilots could still fly the airplane. The elevators answered and the jammed stabilizer happened to be close enough to a usable position. Flight 261 climbed over Mexico and continued toward California with 88 people aboard. What the crew could not see was the condition inside a screw and nut assembly at the top of the vertical tail. Its threads had been wearing away. They needed grease to keep two loaded metal surfaces apart. The maintenance interval for that grease had grown from 500 flight hours to an average of about 2,550. A separate wear check had also been pushed farther apart. The airplane had passed through both systems and returned to service. Near Los Angeles, the jam released into a dive. The crew recovered. Minutes later, the remaining thread material could no longer hold the stabilizer. The tail shifted beyond its normal range, and the pilots lost the ability to keep the nose where they commanded it. Flight 261 entered the Pacific north of Anacapa Island. There were no survivors. The official investigation would trace the failure through recovered metal, flight data, and years of maintenance decisions. It found no single moment when someone knowingly accepted a doomed airplane. It found something more ordinary, a critical component losing its safety margin while intervals, measurements, approvals, and assumptions all said the aircraft could keep flying. On an MD-83, pitch control begins with two different surfaces. The elevators move quickly at the rear of the horizontal tail. They answer the control columns in the cockpit and point the nose up or down. The larger horizontal stabilizer changes the neutral position around which those elevators work. It trims away a force that would otherwise remain in the pilot's hands. The stabilizer does not rotate around a simple hinge. Near its forward attachment, a motor turns a long steel jack screw. A bronze Acme nut travels along those threads. Because the nut is connected to the stabilizer, its movement changes the angle of the whole tailplane. A small motion at the mechanism becomes a large aerodynamic force outside. During normal operation, the screw carries heavy tension while the nut threads spread that load across their contact surfaces. Grease matters because those surfaces slide under pressure. A proper film of lubricant reduces friction and carries debris away. Without enough of it, each movement can remove a little more bronze from the nut. The missing metal does not grow back between inspections. Engineers monitored that loss with an end play check. Technicians restrained the stabilizer, applied load in opposite directions, and measured how far the screw could move inside the worn nut. The service limit was 40,000ths of an inch. The number was small, but the check was designed to expose a space that should not keep widening. The mechanism depended on maintenance to keep wear below that limit. It did not have a second structural path that could safely carry the stabilizer after all the nut threads were gone. The design assumed that lubrication and inspection would prevent complete loss. If those defenses failed together, the airplane would reach a state the flight crew could not repair from the cockpit. Alaska Airlines began operating MD-80 aircraft in 1984. Its maintenance program was approved and monitored by the Federal Aviation Administration. Like every large program, it translated thousands of physical tasks into intervals. A job could be due after a number of flight hours, after a calendar period, or as part of a larger check that kept the fleet moving. In 1987, Alaska scheduled jack screw lubrication every 500 flight hours. The interval later became 1,000, then 1,200, then 1,600 hours. In 1996, the task moved to an 8-month calendar interval without a flight hour limit. At the airline's rate of use, 8 months averaged roughly 2,550 flight hours. Extending an interval does not mean removing maintenance, it means betting that the task remains effective for longer. If every lubrication is thorough and the grease lasts, the added distance may appear uneventful. If one application is missed or incomplete, a long interval gives dry contact more time to become damaged before the next scheduled chance to find it. The FAA approved the changes. That approval matters because the regulator did not merely arrive after the accident to judge the airline. It had accepted the maintenance program as it evolved. Airline data, manufacturer guidance, and federal oversight were meant to restrain one another. In this case, the interval became longer while the mechanism still depended on grease as its first defense. Flight 261's jack screw had been lubricated in September 1999, about 4 months before the crash. The calendar said the next task was not yet due. The wreckage said the interface had not received effective lubrication. Investigators could not turn that difference into a reliable account of one person's actions. They could say the system had allowed severe wear to continue. Lubrication was only one defense. The end play check was supposed to reveal the wear itself. It did not need to know why metal was disappearing. It only needed to show that the gap had grown too large and forced the assembly out of service. But a measurement is only as dependable as its fixture, its procedure, its interval, and its record. The accident airplane's last required end-play check occurred during a heavy maintenance visit in 1997. Evidence about how it was performed was incomplete and conflicted. Investigators examined the restraining fixture, technician accounts, and the numbers associated with the work. They could not determine whether a non-compliant fixture caused an inaccurate measurement or contributed to the accident. That uncertainty has often been flattened into a story about one mechanic and one bad reading. The NTSB report does not support that clean accusation. It describes a check that could be sensitive to technique, a maintenance environment with weak controls, and a result that did not remove an assembly later found catastrophically worn. The failure belongs to the system around the measurement. The interval for the check had also expanded. By the time of the accident, Alaska's approximate interval was 9,550 flight hours. A wear check can catch a condition only when it occurs before the condition becomes dangerous. Moving it farther apart increases the amount of deterioration that must remain predictable between one reading and the next. Before the crash, in-limit end-play values were not required to be recorded and tracked in the way later directives demanded. That meant the maintenance system had fewer trend points. A component could be technically inside a limit at one check without anyone seeing whether its rate of change had accelerated. A threshold can remove a failed part. A trend can expose one approaching failure. On January 31st, 2000, N963 AS arrived in Puerto Vallarta from Seattle. The inbound crew reported no stabilizer problem. Captain Ted Thompson and First Officer William Tansky took over for the return trip. The MD-83 carried 83 passengers and 3 cabin crew members. Its planned route led to San Francisco, then north to Seattle. The flight left at about 1:37 in the afternoon. 12 minutes later, climbing through roughly 23,400 feet, the stabilizer moved from 1/4 degree to 0.4 of a degree, airplane nose down. The change was small enough to look ordinary on a graph. It was the last recorded stabilizer movement before the first dive. As the aircraft climbed, the pilots found that electric trim would not move the stabilizer. The cockpit voice recorder begins later, so there is no complete recording of their first diagnosis. What the data shows is a jammed mechanism and an airplane that remained controllable. The elevators could compensate, but they had less room to work as speed and configuration changed. For much of the flight, the stabilizer stayed in that fixed position. The crew continued north, worked checklists, and contacted maintenance as radio coverage allowed. A fault that can be managed for hours creates a difficult judgment. It proves the airplane can fly now. It does not prove the condition will remain fixed through descent, flap extension, and landing. The crew discussed possible airports and the demands of landing. San Francisco had operational constraints. Los Angeles offered long runways, better weather, and immediate company support. Dispatch expressed concern about the disruption of landing away from San Francisco. The captain answered that he was concerned about flying past suitable airports. Flight 261 turned toward Los Angeles. The NTSB later called the decision to divert to Los Angeles prudent and appropriate. That finding matters because the destination argument can distract from the failed mechanism. The crew did not create the worn threads by changing course. They moved toward an airport with more options while trying to understand a control problem the airplane's checklists did not fully explain. They wanted to know how the airplane would behave at lower speed. Slowing for landing changes the forces that the elevators and stabilizer must balance. The crew asked for a block of airspace over the ocean so they could test the configuration away from traffic and populated ground. The decision put Flight 261 west of the coast near the Channel Islands. Maintenance personnel discussed possible ways to free the stabilizer. The crew had already tried normal and alternate trim. Circuit breakers were checked, the jam remained. From the ground, the condition could still resemble an electrical or mechanical obstruction. Inside the tail, the surviving nut threads were carrying loads across a badly worn interface. This difference between symptom and condition controlled the next minutes. A jam suggests something that may release. Severe thread loss means release can be dangerous because the structure may move into the space the missing metal once occupied. The pilots had no gauge showing Acme nut wear, they had a wheel that would not turn, and an airplane that still responded to their hands. At about 4 o'clock, Flight 261 began descending toward the Los Angeles area. The pilots prepared to extend the flaps in stages and observe the controls. They were not performing an air show or a reckless experiment. They were trying to discover whether a damaged airplane could be configured for landing before committing to the runway. Just after 4:09, the crew tried the trim again. The jack screw began turning. For the first time since the climb from Mexico, the stabilizer moved. The recorder showed 2.5 degrees, airplane nose down. Later modeling placed the actual angle near 3.1. The aircraft pitched over. The pilots pulled on the control columns. The elevators moved against the stabilizer's new angle while the airplane descended. Together they applied heavy force and arrested the dive. Flight 261 lost several thousand feet, then returned to roughly level flight. The recovery was real. So was the damage that had just announced itself. In the cabin, the upset had thrown loose objects and injured people. The crew told controllers they had a flight control problem and needed room. Outside, another aircraft was asked to observe Flight 261's tail. Nothing obvious could reveal the missing thread material from a distance. The MD-83 still looked complete as it flew above the ocean. The first dive changed the problem. Before it, the stabilizer had been jammed near a manageable position. After it, the stabilizer sat farther nose down, and the pilots needed sustained elevator force to hold the airplane. They discussed the control pressure, the flap setting, and how to reach the runway. Each choice now altered the load in the tail. Then they recovered because some structure still restrained the stabilizer. Investigators later found that the torque tube inside the Acme screw could catch the nut assembly after the threads failed. Tail fairing brackets also limited movement for a time. These were not designed as a safe backup. They were parts taking loads they were never meant to carry this way. The cockpit voice recorder preserved the final 31 minutes. Its transcript is difficult to read because the pilots remain practical. They calculate, test, and coordinate. There is no point when the evidence becomes a speech about fate. The recorder captures professional work continuing inside a problem whose decisive damage had happened long before the microphones began recording. Captain Thompson was 53. First Officer Tansky was 57. Both held airline transport certificates and had extensive experience in the DC-9 and MD-80 family. The investigation found no evidence that fatigue, drugs, alcohol, or an unrelated medical event explained the crash. The crew's difficulty came from the airplane they were trying to control. Their actions also reveal the limits of a checklist. A checklist can isolate electrical power, choose alternate trim, and specify landing considerations. It cannot restore bronze that has been ground from a nut. Once the physical support was gone, no sequence of switches could give the stabilizer a new load path. Procedure had reached the edge of design. The controllers moved other traffic and prepared Los Angeles for the emergency. The crew asked the cabin to prepare. They continued discussing speed, flaps, and the forces on the controls. Around them, the air traffic system was creating space. Inside the tail, the margin was shrinking toward a second release that outside support could not prevent. For investigators, this interval would become a synchronized record. Every change in pitch, roll, speed, flap position, and control input could be placed beside the cockpit audio. That precision makes it possible to explain the mechanics without inventing what anyone felt. It also shows how quickly the final structural sequence moved once the remaining restraint failed. At 4:19, the crew was adjusting the flaps and trying to reduce the force needed to hold level flight. At 4:19:36.6, the cockpit recorder captured what the report calls an extremely loud noise. Radar detected small returns near the airplane. The tail fairing and supporting brackets were failing under aerodynamic load. The stabilizer was no longer held near 3.1 degrees nose down. It moved much farther. The airplane's pitch rate reached nearly 25 degrees per second. Within seconds, the load factor went negative and the nose fell through the horizon. The pilots pulled against a surface whose leverage had moved beyond the elevator's ability to cancel it. By about 4:19:45, Flight 261 had rolled inverted and descended through roughly 16,400 feet. The pilots used elevator, rudder, thrust, and speed brakes, searching for any combination that could arrest the descent. Their control inputs continued to the end of the recorded data. The airplane did not return to a stable attitude. The final sequence lasted about 80 seconds from the loud structural event to the end of the recorder. That is long enough to require continued action and too short for another aircraft or controller to intervene. The MD-83 remained near inverted over the water. At about 4:21, it struck the Pacific north of Anacapa Island. Search aircraft and vessels reached the area. The impact was not survivable. Recovery teams worked in the channel while investigators began collecting fragments across the debris field. The film does not need to recreate the moment of death. The evidence begins with what the ocean returned: metal, recordings, and a maintenance history that could be read backward. The recovered jack screw assembly carried the clearest physical clue. Investigators found thin metallic strands wrapped around the steel screw. Laboratory analysis identified material from the acme-nut threads. The nut had not simply cracked into one broken piece. Its load-bearing bronze had been worn and displaced until the screw no longer had intact threads to engage. Tests examined grease residue, wear patterns, torque, thread strength, and possible failure modes. Investigators considered whether the threads fractured suddenly, whether corrosion or manufacturing defects played a role, and whether the assembly had been lubricated with incompatible grease. The evidence pointed back to excessive wear caused by insufficient lubrication, not a hidden one-time fracture. The flight data then explained the sequence. The stabilizer jammed during the climb. It stayed fixed until the first dive. That movement was consistent with thread failure and temporary restraint by other parts of the assembly. The final loud event matched failure of the remaining brackets and the stabilizer's movement beyond the range the airplane could survive. This reconstruction did not depend on one dramatic photograph. It came from agreement between different records. Metal showed the lost threads. The recorder showed the crew's problem. Flight data showed the stabilizer and aircraft response. Maintenance documents showed how long the defenses had been spaced apart. Each source narrowed what the others could mean. The probable cause followed that chain. Flight 261 lost pitch control because the horizontal stabilizer trim jack screw assembly's Acme nut threads failed in flight. The failure came from excessive wear caused by insufficient lubrication. The wording is mechanical and exact. The contributors explain why that physical condition was still aboard a passenger flight. The first contributor was Alaska Airlines' extended lubrication interval and the FAA's approval of that extension. A longer interval increased the chance that a missed or inadequate lubrication would allow severe wear before the next task. The finding joins operator and regulator in one sentence because the maintenance schedule belonged to both operation and oversight. The second was the extended end-play check interval, again with FAA approval. The check was the independent chance to find wear after lubrication had failed. As that chance moved farther away, the program placed more confidence in assumptions about wear rate. The accident assembly wore far beyond the condition the program was supposed to keep in service. The third contributor was design. The trim system had no fail-safe mechanism to prevent catastrophic effects after complete loss of the nut threads. Certification treated maintenance and inspection as protection against that condition. It did not adequately require the aircraft to remain controllable after the protection failed. Wear had become a catastrophic single point of failure. Post-accident FAA inspection of Alaska's maintenance program found procedures not consistently followed, weak controls, unclear responsibility, and quality systems that did not reliably close the gaps. Those findings describe an organization, not one careless pair of hands. Work cards, supervision, training, record-keeping, and surveillance decide whether a correct instruction becomes a correct physical result. The failure crossed corporate boundaries. McDonnell Douglas had designed the system. Boeing held the design after the companies merged. Alaska maintained and operated the airplane. The FAA approved and surveilled the program. No boundaries stopped the wear. Each institution controlled a different defense, and the aircraft carried the combined result. The first response was inspection. Regulators ordered operators to examine jack screw assemblies, measure end play, and report results. Aircraft with unacceptable measurements had to be removed from service. The accident had turned a hidden maintenance task into an immediate fleet question. How much wear existed in the tails of other airplanes built around the same assumption? Airworthiness Directive 20001-515 set a lubrication interval of 650 flight hours and an end-play check interval of 2,000 hours for affected aircraft. It also required measurement reporting. The new numbers did not restore Flight 261. They shortened the distance between defenses and created data that could show how an assembly was changing. The NTSB also asked the FAA to address procedures, fixtures, overhaul practices, surveillance, and certification. One recommendation was broader than the MD-80. Safety analysis needed to consider wear-related failures in primary structures and flight controls, not only clean fractures or failures that arrive without a long maintenance history. Maintenance programs often improve by extending tasks when service data shows that shorter intervals are unnecessary. That work is not inherently unsafe. The lesson from Flight 261 is that an interval cannot be separated from task quality, measurement quality, and failure consequence. The more a design depends on maintenance, the more carefully the system must verify that maintenance worked. The MD-80 family continued flying safely for years after the accident under revised requirements. The point is not that the aircraft type was secretly uncontrollable. It is that one control mechanism had been allowed to reach a condition its design could not tolerate. Safety returned through shorter intervals, better measurement, stronger oversight, and attention to the failure mode. The technical language can make the loss sound smaller than it was. 88 people boarded in Puerto Vallarta. Some were returning from holidays, others were traveling for work or going home. 5 crew members were responsible for an ordinary scheduled flight. Every maintenance interval and certification assumption eventually arrived in the same cabin with them. The pilot's final actions are sometimes remembered because the airplane rolled inverted and they kept trying to fly it. Their effort deserves accuracy, not myth. They did not conquer the failed stabilizer, and they did not stop working. The record shows control inputs through the final seconds. It cannot tell us what the people behind the cockpit experienced. Families pressed for answers while investigators worked through an unusually technical chain. Mechanical detail did not reduce responsibility. It made responsibility specific. Grease application, interval approval, fixture design, trend data, and fail-safe structure were not background paperwork. They were the means by which a passenger airplane was supposed to remain controllable. Anacapa Island remains visible from the Southern California coast on a clear day. The wreckage field lay in deep water north of it. There is no need to turn that location into a dramatic landmark. Its importance is simpler. A flight headed for a prepared runway ended within sight of land because a hidden load path had already been reduced past recovery. The loss belongs to the families, but the evidence belongs to every system that schedules safety work. A task marked complete is not the same as a protected component. An approved interval is not the same as a safe interval under every failure. Flight 261 made those distinctions impossible to ignore because the physical record survived to show them. The jack screw assembly was built with strength far above normal flight loads when its threads were intact. That strength did not protect it from years of wear without reliable detection. Safety margin can exist in material, in inspection, in design, or in oversight. Flight 261 exhausted several kinds of margin in sequence. Investigators could identify the probable physical cause with unusual precision. They could not reduce the history to one villain or one knowingly fatal choice. The maintenance interval had been extended in steps. The wear check had not stopped the aircraft. The regulator had approved the program. The design had no safe answer after total thread loss. That is what makes the accident useful to study and difficult to tell. Each decision can sound reasonable when isolated. A longer interval. A measurement inside a limit. A design protected by maintenance. An approval based on the program presented. Put together, they left 88 people flying above the Pacific with bronze threads that could no longer hold the tail. After Flight 261, the intervals became shorter, measurements became reportable, and the failure mode entered certification and maintenance practice. Those changes are the proper memorial inside the system. They do not make the crash inevitable in hindsight. They show that the defenses could have been built differently before the final flight. A passenger airplane is held in the sky by visible wings and thousands of hidden agreements. Flight 261 was lost when one of those agreements, between a steel screw, a bronze nut, and the system meant to protect them, failed in full view of no one. Coldwake follows the evidence left behind because hidden failures become preventable only after someone learns to see them.